Hello. Today we're going to talk about the chain rule in 3.3. We discussed the basic rules in 3.1, including the power rule. In 3.2, we talked about the product rule and the quotient rule. Today we got another rule, the chain rule, which is used for differentiation of composition of functions. Suppose h is a composition of two functions, g and f. So h of x equals g of fx. Then the derivative of h with respect to x, h prime, equals h g prime times f prime. So you need to take the derivative of both g and f and multiply them together. When this h is a power function of f, so h of x equal to f of x to the nth power, then you can use the chain rule to get the derivative of h, which is n times f of x to the n minus 1 times f prime. Okay, let's do some simple examples. Suppose capital F is equal to 3x plus 1 squared. We need to find the derivative of this function. First, remember, this function is a composition of two functions, where the product you take the square is a function itself. So in this case, f of x equals 3x plus 1 and n equals 2. So using the chain rule, we got f prime equals 2 times 3x plus 1 to the 2 minus 1 times the derivative of 3x plus 1. So we get 2 times 3x plus 1 times 3, which is 18x plus 6, if we simplify it. We can also use another approach to take the derivative. Namely, we can expand the function first and then take the derivative. So if we do that, for 3x plus 1 squared, you get 9x squared plus 6x plus 1. And just use the power rule to get f prime x equal to 18x plus 6. So we got the same answer by using the chain rule and the direct differentiation. All right. Let's do another example. Suppose capital G of x equals square root of x squared plus 1. We need to find the derivative of this function g. So the first step to do is always to rewrite the function in the exponential form. And this is always true when you get some radical functions. Now, we can recognize that the function f in this case will be x squared plus 1. This is a composition of two functions again, and n equals 1/2. So using the chain rule, we got the g prime equals 1/2 x squared plus 1 to the 1/2 minus 1 times x squared plus 1 prime. So we got half times x squared plus 1 to the negative half times 2x, and you can simplify it by rewriting it in rational form. So we got x over square root of x squared plus 1 at the end. All right, let's do a problem that requires both the product rule and the chain rule in one problem. In many problems, you might need to use multiple rules instead of one. So in those cases, it is especially important to remember the chain rule, because it is very easy to skip this rule when you do the problems. So in this problem, h of x equals 2x squared plus 3 to the 4th times 3x minus 1 to the 5th. And we need to find the h prime. Okay, the first step is to use the product rule, because you can recognize this function as a product of two parts, namely the product of 2x squared plus 3 to the 4th times the product of 3x minus 1 to the 5th. So you do the product rule first. So If you still remember the rule, you take the derivative of the first part times the second part plus the first part times the derivative of the second part. So then we get 4 times 2x squared plus 3 to the cube. But we still need to take the derivative of the function 2x squared plus 3. That's the inner function. So we are using the chain rule in here. And then multiply 3x minus 1 to the 5 plus 2x squared plus 3 to the 4th times 5, 3x minus 1 to the 4th. Multiply the derivative of 3x minus 1. Again, we are using the chain rule in here because 3x minus 1 itself is a function. So we got the 4x from the derivative of 2x squared plus 3 and 3 from the derivative of 3x minus 1. So we can do a little simplification for the result. We can factor 2x squared plus 3 to the cube times 3x minus 1 to the 4th. And that will leave us 4 times 4x times 3x minus 1 for the first part, and 2x squared plus 3 times 5 times 3 to the second part. And then we can multiply out the inside of the last part and the combined like terms to get 70x squared minus 16x plus 45. So that's the final answer. This is for today.